This chapter we're going to take a look at still ionic and molecular compounds, but we're going to look at them in a little bit more detail and less about their names. So this is actually a pretty big review chapter, so you want to make sure and take advantage of these quote-unquote easy points here. So we're first going to look at ions. So to review, our valence electrons are the electrons in our highest occupied energy level. And so we sometimes think of these as the electrons in the outermost energy level. And these are the electrons that are responsible for giving elements their chemical properties. So how many valence electrons are in each of the following configurations? So if we look at the table below, we look for our highest principal energy level to figure out how many valence electrons. And so remember, these little superscripts are telling us how many electrons are in each level. So for lithium, we have 1 valence electron because the highest energy level is 2, and the little 1 shows us that there's 1 electron in that level. When we look at beryllium, again, the highest energy level is 2, so we look at how many electrons are here, and beryllium has 2 valence electrons. Nitrogen, again, has the highest energy level as 2, but this time that 2 shows up in 2 different places, and so what we have to do is we have to add the electrons together. So in nitrogen's case, we have 5 valence electrons. Again, neon's the same way. That highest energy level shows up twice. So we simply add together the valence or the electrons in those 2 areas, and we see that there's 8 valence electrons. So valence electrons for the S and P blocks follow the number of the group in the S block. So the first the first column has 1 valence electron, and the second has 2 valence electrons. And then when we look at the P block, we take the group number minus 10. This is all something we've kind of worked with already. So I believe we've also looked at electron dot diagrams, and these diagrams show us the valence electrons in each element. And so the electrons are shown as dots around the element symbol, and so I think we've done these before. And so for lithium, it's got the 1 valence electron, and we see that with 1 dot. Beryllium has 2 valence electrons, and so it has 2 dots around it. Boron is in group 13, and so to figure out the valence electrons, you subtract the 10, and there are 3 valence electrons, which we can see as the 1, 2, 3 dots around boron's element symbol. Carbon has 4 valence electrons because of the minus 10, and 1, 2, 3, 4. So when you draw these electron dot diagrams, what you'll notice is that it's kind of like there's a box around the element symbol, and the electrons are placed on those 4 sides, and they will be placed as far apart as possible. So if there's 2 valence electrons, it's not going to double up on the same side right away. So that's not correct. What's going to happen is they're going to be placed as far apart as possible. It could be across the sides or top and bottom. And this is because like charges repel each other, so they're going to want to be as far apart as possible. Eventually it will get to the point like in nitrogen where there's 5 valence electrons, and so you place 1, 2, 3, 4, and that 5th one is going to have to start pairing up. And that's okay once you get to that point of needing that extra space. Noble gases are unreactive, and this is because of their electron configuration. This is because they satisfy the octet rule. This states that elements tend to form compounds in ways that give them 8 valence electrons, because this gives them that noble gas electron configuration. So the ways to satisfy this octet rule is to either share valence electrons or to transfer the valence electrons. If elements are going to transfer valence electrons, the metals, so the elements on the left side of the periodic table, will tend to lose the valence electrons, and nonmetals will tend to gain valence electrons. Again, this should be review for us. So when we lose electrons, we form positive ions, which we call cations. And so we can see this in sodium. Sodium's original electron configuration gets us up to 3s1, so our valence electron is in the third energy level. And so that electron will actually be lost when sodium forms an ion. And so we can see that here sodium has gained that positive charge and it has lost the electron. And so its new electron configuration reflects the loss of this electron. And notice how the 3s1 is no longer being shown. And that's because that 3s electron has been released right here. So isoelectric is something that describes two atoms or ions that have the same electron configuration. So this is kind of a new topic right here. So the prefix iso means equal. So they have equal or the same electron configuration. So when magnesium goes from having those 3s2 valence electrons and it loses the 2 electrons to form Mg2+, its electron configuration is now 1s2, 2s2, 2p6. And then if you look at aluminum has the 3 valence electrons, and when it loses its 3 valence electrons to become Al3+, its electron configuration is 1s2, 2s2, 2p6. And so these two electron configurations, or these two ions, Mg+2 and Al+3, they have actually the same electron configuration, and so we call those two ions isoelectric. And this is just another way. We have our 1 valence electron, and now we have a positive ion, and here is that valence electron being released. This is just a way to show the loss of an electron. It's just, like I said, another way to write it. It's the same as this up here. It's just another way to write it. So the opposite of losing electrons would be gaining electrons. And so this creates a negative ion, which we call an anion. And so here we have fluorine. This plus is showing us that we're gaining that electron. And here is how we write that as a product, F-. Then we have our electron configuration for fluorine, 1s2, 2s2, 2p5. And then our 2p5 becomes a 2p6 to show us that we gained that electron. Same with oxygen here. Our electron configuration for oxygen, 1s2, 2s2, 2p4. But now we're gaining 2 electrons, so our 2p4 becomes 2p6. And then nitrogen, 1s2, 2s2, 2p3. Nitrogen gains 3 electrons, so this 2p3 becomes 2p6, and so we have nitrogen 3-. And so all 3 of these ions, you'll notice that their electron configurations are all the same, so that makes all 3 of these isoelectric. And here's just your periodic table basically showing you that this first family is all +1s. The second family here is all +2s. Here we have that 13th column is all +3s. This 4th column is a little weird. The top 2 have really no charges because they don't transfer electrons, where the bottom 3 are kind of transition metal-ish. here in the nitrogen family, -3. Again, the bottom is a little different because there's some transition metals in there. And then we have -2, except this last one. And then lastly, we have a -1 charges. So this is just to remind you of these charges. I think we've been working with these enough that for the most part, this is pretty well ingrained in you guys. So then when we look at our transition metals are located in the D block, and they can hold up to 10 electrons. It's hard to lose enough electrons to achieve noble gas configuration. And so many transition metals will have multiple ions with different charges. And so we kind of know this when we look at iron. Notice that they wrote it in noble gas configuration. Iron has these 2 valence electrons. And so it can lose those 2 valence electrons and get to 3d6. Or it could actually lose one of these D electrons and end up as 3d5 with a loss of 3 electrons. So remember, according to the Aufbau principle, that the electrons fill 4s before the 3d level. So the s electrons are always going to be the first ones to be removed when forming the forming the ions, because the 4s electrons are the outermost, for sure, valence electrons. So this gives a charge of +2 for transition metals. It's very common. So a half filled D sublevel is also particularly stable. And so if a transition metal has very few electrons in the D sublevel, like scandium, it can also achieve noble gas configuration because it can start to lose those D sublevel electrons fairly easily. And then zinc and copper can actually achieve a full D sublevel. As you can see here, they're at the end and have that 3D, and once they lose the 4s electrons, they become, they have this 3D electron configuration. We call this a pseudo noble gas configuration, and this is particularly stable as well. And so a pseudo noble gas electron configuration has 18, so to speak, valence electrons, or kind of what appears to be 18 valence electrons. It will have S2 full, it will have P6 full, as well as D10. And so if you were to write out these 2 electron configurations instead of using the noble gas argon, you would see that it has the full 4s2, 4p6, and that 3d10. So we get 2 plus 6 plus 10 for 18 electrons. And so that's what we call a pseudo noble gas electron configuration. And I believe in your assignment, you will see that you have to, for number 11, state whether it has a noble gas configuration, a pseudo noble gas configuration, or neither. So when you're looking for that pseudo noble gas electron configuration, you're going to be looking for the outermost S sublevel being full, the outermost P sublevel being full, and the outermost D sublevel being full. So all 3 of them would need to be full in order to have that pseudo noble gas electron configuration. The regular noble gas electron configuration would have just 8 valence electrons.